This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
Hello, hello. Good afternoon. My name is Susan Hackwood, and I'll be moderating this next section. And this is the next to last one before us and cocktails. We have a spectacular group of people who will be talking. But first, before we go forward, let me tell you something about the secret life of Charlie Kennel. Okay, so... You know, I was listening yesterday and today, and in my career in engineering, I've touched on some of the subjects that were being talked about, but it was absolutely wonderful to be with the people who were really there and generating those new ideas. I felt like I was in an Entmoot, you know, which is in Middle-earth, where all the sage trees get together and discuss the future of the universe. So it was a wonderful experience. I've had the pleasure of working with Charlie for a decade or so now, maybe longer. And I work with Charlie in a totally different context. So can I just take 2 minutes to put that in context for you? This is part of Charlie's secret life. Charlie is the chair of the board of directors of the California Council on Science and Technology. And the council was formed in 1988, and it's modeled after the National Research Council. And the basic goal was that we have so many really good scientists and engineers and medical doctors, et cetera, in California. And there's really a vacuum in how that body of knowledge is used in policy making, particularly in the state government. We're good at sending people to NASA or sending people to Congress or sending people around, but we're not good at sending people to Sacramento. Yet there's so much in charge of our future, and particularly of our infrastructure and what goes on. So the council was created. It's an amazing organization. It represents about 250 people of the state's science and technology leadership. Julie Meyer-Wright, who's in the audience over here, is one of our council members, and I don't know where Bob Dines went, but Bob is one of our senior fellows. Okay, one of our senior fellows. So we represent people at the highest distinction, and we give them a focus of getting their information through to policymakers who are making decisions. So great group, and we've been talking a lot about the past, the history of Charlie's work. Well, let me tell you something that's really current. I mean, current like as of today. So yesterday, our organization released a report on hydraulic fracturing. This was a report that was commissioned by the Bureau of Land Management, and Charlie, as chair of the board, was deeply involved in making sure that we had really good science, and we had only science that was verifiable, peer-reviewed, conflict of interest removed, and all the things that we know how to do as scientists. And Charlie was really in charge of that. And as of today, Charlie, today it's in 60 media outlets. It's in the LA Times, it's in ABC News, it's NPR, it's all over the place. And as a consequence of the work that was done, and the Bureau of Land Management has announced that it's going to start relicensing for hydraulic fracturing starting in 2015. And it's based on the data that we said that we knew, but more importantly, the data that we said that we didn't know. Because this report clearly says what we don't know and what we need to measure going forward. And so it's just come out that the Bureau of Land Management is going to go forward. This work is built on a whole bunch of reports that Charlie was also involved with. We've talked a lot about greenhouse gases and about energy and about the future of climate change. So we've done a whole series of reports which translates the science into the policy and looks at it through the eyes of policymakers such as those who created AB 32, the greenhouse gas emissions legislation, and also for the executive order that we're looking at. And the most important thing here is that we do a systems engineering approach, because we look at the whole system. We don't look at anything in isolation. You can only count an electron once. So we look at the whole system going through, and this work has resulted in not only legislation, policy changes, business changes, all sorts of things. So the council is fortunate enough to do profound things. We also do things that we didn't really want to do, but we had to, like look at the efficacy of detecting cell phones in prisons, for which we went around the prisons in California. So we will do anything that the state is asking us for. And most important over the last few years, and this is under Charlie's leadership, we've started a program where we place 10 recent, fresh PhD graduates from science and technology into state legislative offices, where they get to learn how the sausage is really made. They become the advisory, science advisory for that committee or for that legislative office. And they come from all over the place. They come from our best schools, Berkeley, Carnegie Mellon, Cornell, Columbia, you name it. We've got students who have come through here and gone through this process. And what's interesting is that more than half of them, more like 70% of them, stay in public policy. They switch from a promising career in science or technology and stay in public policy. Why? Because they see how much they're needed. They are responsible for literally hundreds of pieces of legislation and even more hundreds that don't get passed. So along those lines, this is special because Senator Fran Pavley, for any of you who know who she is in the state, she's a very powerful senator. AB 32 came out of Fran Pavley's work, and she is the Senate Natural Resources Committee chair. It's she who has got the legislation on hydraulic fracturing for SB4. And I show this picture because these are her right-hand people. And the young lady who's standing over to her left-hand side is Tony Lee, one of our current fellows, who has her PhD in biochemistry and molecular biology from Caltech. And she's so special, she gets to walk the first dog, Sutter. So that's Sutter. So that's another aspect of Charlie's secret life, where he has truly helped translate the wonderful science that he knows so well into the hands of policymakers who can actually use it and become a known and trusted entity in that. So great. We were given the task in this session to talk about the technologies and science of the future. And I use this analogy. When I was at Bell Labs, we talked about pots and pans. So pots and pans are plain old telephone service, and pans is pretty amazing new stuff. So we're going to get to talk about some pretty amazing new stuff now with our speakers, and then have a roundtable discussion afterwards. And many of you know the kinds of things that are the disruptive technologies that are truly affecting us now. This is from a McKinsey report. I won't read these things, you can see them, but you know that these are the things that are deeply affecting everything we do in society and everything that we do in our life. I'll give you just a couple of examples. This is from the MIT Sensibility Lab, and what it is showing how mobile networking is redrawing communities. So, and Larry, you know a lot about this, but the bottom one is a density map of the population in the US. The second one is the frequency of connections of cell phone and text messaging between communities. And the top one is a density map projected up onto that. And you can see that the United States is changing its boundaries. And we can confirm that Northern California does not talk to Southern California. We can also confirm that Texas talks to no one. And we can also see that the East Coast and West Coast, the coasts have got a close connection. So those are the sorts of things that are redefining our society. Everything we do, how we connect with people, is changing. Our young people have got a very different way of introducing each other. And there's no such thing as a blind date anymore. We also have come to rely on machines in a different way. So do you remember Clippy? Yes. Clippy, 2003, Clippy came out. In 2010, Time magazine voted it as one of the 3 worst inventions ever. It was dreadful. Remember, as soon as you wrote dear, it would pop up and bug you. So we've gone from that to Samantha and Siri. Anyone see the movie Hair? Yes. Okay, so in Hair, the protagonist is love forlorn and falls in love with his system on his cell phone. It's basically a Siri, and they have a very strong and long relationship with each other. So it's happening, the changes that we're seeing in society. We're seeing super changes in medicine. Surgical robotics is on the scene, and it's not going to go away. Telemedicine is definitely there. And we're beginning to see the drone wars. And you know how the drones are used in the military, and this is an example. MIT has a little helicopter that you can call up on your cell phone, and it will come and you say, I want to go to lab so-and-so, and the little machine will come and float in front of you and say, oh, you want to go to lab so-and-so? I'll take you. And you follow it, and it'll take you there. So, and you know Amazon is going to use this as drops and things. Yeah, right. So, but this is the kind of society we live in. And I'll finish with this, the genomics with 23andMe and all the other things. And Larry is going to talk about wiring yourself up. You can find all sorts of things out about yourself. So I've discovered that from 23andMe, I have less of a percentage of Neanderthal in my genome than other people. So Steve Jobs was a visionary, and some of you might like him, some of you might not like him, but he got it right about how inventions happen and how creative things happen. And the people that we're going to have now talking are on the forefront of these things. And so in order of where we'll go, we're going to have Louis Branscom's talk first, and on forces of science and technology. We've got Martin Rees, who's going to talk about catastrophes and risks. Larry Smarr is going to talk about digital transformation of medicine. And then Heinz is going to wind us up with technology engine for science and progress. So with that, I'll keep quiet and invite up Louis.
Thank you. Well, I came out to this wonderful La Jolla place in 2005 for very good reasons. When I came along, just to give you a word or two about my background, where I come from, as an emeritus professor in public policy and corporate management at the Kennedy School at Harvard. You may have thought I was a scientist. That doesn't sound much like a scientist, although the corporate management part of that title probably reflects the 15 years I spent as chief scientist and vice president at IBM. In any event, at the Kennedy School, I was the director of the Science and Public Policy program there, following in the footsteps of the great Harvey Brooks. In those days, whenever I was at a meeting and somebody asks, what are you doing? I say, I'm the understudy of Harvey Brooks. I don't know many of you how know him. I think he's now deceased, but I think he's the best and strongest science policy person the United States has had the privilege of enjoying. But that's not where I started. I did indeed start as a physicist. In the third grade, I asked for a book to read. She gave me a copy of Mr. Tompkins in Wonderland by Gamow. If any of you ever read that, you also became a scientist. You couldn't resist it. But in any event, to move on from there, I did my PhD at Harvard. I took on a project that a very good friend of mine tried for his PhD and couldn't do it. But I was a postdoc, so I figured, of course, I can do that. I tried to build equipment that would do this experiment. Too hard for a university. I went to the Bureau of Standards, where they had marvelous facilities. And after a considerable period of time, I was able to put together the first cross-beam device that could do the spectroscopy of a negative ion. And the reason for wanting to do that is to determine what are the frequencies of light that will detach an electron from a proton with two electrons on it instead of the one it's supposed to have. The reason for doing that is that there had been a theoretical proposal that the explanation for the wavelengths and the temperature of the solar photosphere would be determined by the absorption and reattachments of the negative ion of hydrogen. But nobody had ever made a measurement of that, and it really was not proved. And the theory was later from Chandrasekhar got to be done very well, but at the time it wasn't all clear. And so I was successful, along with colleagues, in doing that experiment. And for 10 years, we did studies of negative ion physics of one kind or another. But at the end of the 10 years, something very dramatic happened. It turned out that in this apparatus, the only way you could do the experiment was to get as much light intensity as you possibly could. I did all kind of crazy things to do that. But at the end of the 10-year period, all of a sudden, you could now get tunable lasers. The tunable laser at that time had 10 to the 13th power more intensity than the best light bulb I had. And so that then transformed negative ion spectroscopy. I turned it over to the chemists. And then I turned my own career back over organizing and doing, continuing my science, but organizing the one thing I did I'm most proud of, which is the creation of an organization called JILA. The original name, which I gave it, was the Joint Institute for Laboratory Astrophysics. And it was done by Dick Thomas and myself, an astrophysicist, and myself. And this wonderful institute in Boulder has, since we put it together, won 3 Nobel Prizes, none of which I earned. But I'm proud of the organization that stimulated that wonderful success. So that then gets me to the question of going then, after I retired from there, going back to Harvard in order to teach and run the science and public policy program. Now, almost all of the speakers have said wonderful things about Charlie, and I could do that too, about his scientific achievements. But nobody has pointed out what a brilliant manager he is. Of course, those of you who work for him here probably know that. But when I came out here in 2005, I went to see Charlie, and he was very generous, and he offered me a position in SIO. He explained that if I'd like to get a professorial position here, he's sure he could do that. It would take 2 years to go through the process here at the university. But on the other hand, if I didn't want to wait 2 years, he could make me a research associate in 30 seconds. And I said, that's for me. So he saved himself A, money, B, time, and my pleasure. That's wonderful. So let me now turn to the task that I was given, which is to say something about the future of science and technology. And I'm going to try to do that, but I warn you, I don't have any pretty diagrams and I don't have any tables with numbers because I don't know what the future of science is going to be. However, as you'll see from this title slide, it's obvious that science does not have a future on its own. It will be dependent, and it always has been, to a considerable extent, on what the socioeconomic environment is, and that's changing just as fast as science is, in fact, at about the same rate, I would imagine. So here on the left is my assertion of at least a few of the important things that I believe is happening and will happen to a greater extent in the future. The most obvious one is the globalization in all kinds of things, not just the economic issues. The economic transition, I think, is underway. I believe there will be new sources of innovation, or at least newly emphasized, and that's going to have effects, which I'll talk about in a few minutes. The government funding, I believe, has been shrinking, especially in basic research, and I'm concerned about that. On the other hand, we've noticed that private sector funding of research, not basic research in most cases, has been growing. That balance I'll say a word about. Climate, obviously, the climate change obviously is going to be a major and increasing driver of research, both public and private, and their relationships with policy. The social and population issues are, I believe, becoming more controversial, especially those coming out of biology. And the last item is to note that the distribution of wealth in this country needs a new improvements in our educational system, because the skills that we require are a big part of the issue, and our education system is not suited to it. Over on the right are a few examples. All of those are familiar to you on the science side as to what's going on. An important issue that's relatively new and going to be dramatically different in the future involves big data. The fact that gene manipulation is now being talked about, being done through bioengineering and manipulation of DNA and the like, that has consequences. Science-based and applied have long since merged. I don't really know how to make reasonable distinctions between those two things. And they're both measuring with the more advanced versions of technology. And finally, there is a transformation already underway, and I think it'll go a lot further in our education system. There's going to be talk in the next section on universities, so I won't say much about it, but I think universities are in for a major evolution that has been very slow in the past and will accelerate for a lot of good reasons. So now let's just say a word or two about globalization. We're all familiar with the way it goes in commerce, but the extent to which companies, even small companies, are evolving into multi-location organizations, picking up each of the smaller companies that have very strong technology, innovative capabilities, and putting them together in an integrated policy. By the way, something that people in China have been doing unusually well recently, at least some of them have. That's a very important part of the issue, and you can see from the statistics there that the U.S. share of global R&D has been declining, so we will face a lot of competition. And that gets me then to the next point, in which there are now a lot of thought, there's now a lot of thought being given by, for example, in the paper by Cole, Glaser, and Lyons, that there will be a very strong desire and need in the United States, as well as in these emerging countries, on what they call synergistic partnerships. The globalization of business, as I said before, is proceeding faster. I think in that case, the emphasis on innovation throughout the world economy is clearly expanding, and that calls for a requirement that the industry in this country has to profit even more successfully on the innovative capability that our science and technology community produce. A few comments about the changes in research support, and in some ways I hope this isn't all true, but I see signs of it. The federal government, first of all, hasn't been very enthusiastic, at least the Congress hasn't. I think the administration would like to be, but the Congress hasn't been very enthusiastic, although there is a lot of vocalization about encouraging innovation. And the second bullet here refers to the proof of concept centers, or POCCs. We have a very good one here in our university. MIT has a good one, but they're very few. And in fact, the president did send a message out to the departments when they put their technical programs together for the budget. They should give emphasis to these organizations. I don't think it's been very successful, but they focus on the valley of death, training graduate students at the mixture of their technology focus, which is where their careers are going, and what they need to know about starting a new company based on their ideas. So the private sector, I think, is going to be under increased pressure, particularly from the more rapidly emerging competitive large countries like China and India. And we'll find that they will need to seek new and more effective relationships with the universities, not in just the typical way of a farmer that goes to a company and sets up a lab and says, okay, we're going to pay your lab and you give us all your patents first choice and so forth. But in much more intimate ways, companies getting in with universities and encouraging the creation of new companies based on new ideas, and therefore stimulating indeed some basic research, which otherwise the industry is not nearly expected to do. On the education side, let me just note the important issue of the relationship between universities and industry. I'm sure that'll be discussed in the next session. And finally, there's an interesting issue on the issue of big data. Everybody thinks about how hard it is to get all that data collected, but the experts in this area tell me the real problem is how do you find the data you want? That's going to turn out to be from the big data. That's going to be a major program. I think it's going to be a commercial service, and now the universities are going to have to go to commercial organizations for a lot of the information that they require. I'm going to skip the biology and just tell you that all of this prediction is my opinion. And in fact, there's a lot of reason to distrust opinions that are not based on fact.
Thank you. About 10 years ago, I wrote a book which I called Our Final Century, ? The publishers cut out the question mark, and when the book appeared in America, they changed the title to Our Final Hour. Americans like instant gratification and the reverse. Well, my theme in this book was that our Earths existed for 45 million centuries, but this one is special. It's the first when one species, ours, has the planet's future in its hands. Over nearly all Earth's history, threats have come from nature. Floods, earthquakes, asteroids, and so forth. But from now on, they come from us. We're deep in what's called the Anthropocene era. These threats are of two kinds. The first are those we are creating collectively, and prime among those is the climate issue which we've heard about this morning. But I want to talk about the second kind, which is caused by the huge empowerment of individuals or small groups by powerful technology. We have an unbalanced perception of risks. We fret too much about minor hazards. Air crashes, carcinogens in food, low radiation doses, and so forth. But we and our political masters are in denial about catastrophic cyber and bio scenarios. The worst of these have thankfully not yet happened. Indeed, they probably won't. But if an event's potentially catastrophic, it's worth paying a substantial premium to safeguard against it, even if it's unlikely, just as we take out fire insurance on our house. The first real human-induced threat, of course, was thermonuclear war. At any time in the Cold War, when stockpiles escalated beyond all reason, the superpowers could have stumbled towards Armageddon through muddle or miscalculation. And the threat of global annihilation, involving tens of thousands of H-bombs, is in abeyance. But there's more reason now, of course, to worry about smaller nuclear arsenals, which could be used regionally, or even by terrorists. But we can't rule out later this century geopolitical realignments leading to another standoff between new superpowers, and a new generation therefore may face its own Cuba, which may be handled less luckily or less cleverly than the last one was. When you remember McNamara and Kennedy said there was a 1 in 3 chance of things going wrong. Well, the H-bomb stemmed from 20th century technology, but we should now be even more worried, in my view, about powerful 21st century technologies. IT and biotech have transformed the way we live. And we are hugely dependent on networks, just-in-time delivery, and other global systems. And in our interconnected world, breakdowns can cascade globally. Air travel can spread a pandemic within days, and social media can spread panic and rumor literally at the speed of light. But as technology offers greater power and promise, in the future, the downsides will get scarier. We're going to get ever more vulnerable. And I think in particular of cyber and bio. Already we know about things like Stuxnet, and they become more serious. And despite the huge promise of biotech, that offers threats too. Within a few decades, millions will have the capability to misuse biotech just as they can misuse cybertech today. Already, there's a great deal of debate about, for instance, these experiments being done on the influenza virus to make it more virulent and more transmissible. One worries about terrorists getting hold of it, one worries about error as well as terror, leakage from labs. And this will get more serious. Freeman Dyson, in a New York Review of Books article, projected that one day children will design and create new organisms just as routinely as his generation had chemistry sets. Well, I think this is far beyond the science fiction fringe. But were even part of his scenario to come about, our ecology and even our species wouldn't survive long unscathed. And my real nightmare is this. It may be possible to make existing viruses more transmissible and more virulent. And it only needs one or two people to cause catastrophe. And for instance, there are many people who think it would be better for the world if there were a few billion fewer human beings in it. Among them are some eco-fanatics with the mindset of extreme animal rights campaigners. What happens when such people have mastered synthetic biology? Techniques to be widespread by 2050. Can we guard against such risk by regulation? The Ancillomar Declaration worked in the 1970s, but now we have a much broader, more international community, more commercial pressures. And so I personally think that anything that can be done will be done somewhere by someone. The global village will have its village idiots, and they will have a global range. And I can't see any way out of this that doesn't cause huge tensions for the competition between freedom and security. And by the 2050, other science fiction nightmares may transition to reality. Dumb robots going rogue, or a computer network that develops a mind of its own and threatens us all. If you think that's crazy, then of course just up, not far from here, there are people like Ray Kurzweil who think there'll be this so-called singularity in 20 years from now, when computers will really completely take over and make superhuman intelligences. That's, I think, a bit extreme, but Ray Kurzweil, of course, is a famous person over here. He's also, incidentally, someone who thinks he's going to live forever. He believes we get to the stage when people can live forever and download their brains into a computer, and apparently he takes 200 pills a day to make sure he can get through to the next 10 or 20 years. And then he has his body frozen. Incidentally, I was once interviewed by something called the Society for the Abolition of Involuntary Death, which is a group here in California which freezes people. And they freeze your body, for a cut price they freeze just your head. And I told them I'd rather end my days in an English churchyard than a Californian refrigerator. And they thought I was very conservative. A deathist, they called me. Yeah. Well, enough for this, but I think clearly we are going to be more empowered by technology, and we'll have a bumpy ride through this century. There may be setbacks to our society, but most of these things won't wipe us all out. But are there any conceivable events that could wipe out all human life? Well, Promethean concerns of this kind were contemplated by scientists working on the first atomic bomb. They asked, could a nuclear explosion set off a chain reaction in the atmosphere or the oceans? I think even Hans Bethe and others thought about this, and they, of course, convinced themselves that there was a huge safety factor. But what about even more extreme experiments? When CERN's LHC accelerator came online, some anxiously asked, could it destroy the Earth? And physicists were pressured to address these speculative existential risks. And in my view, it was right that they were pressed to do this, because it was possible to ask, could physicists unwittingly convert the entire Earth into particles called strangelets? Or even worse, trigger a phase transition that would rip apart the fabric of space itself? There have been theoretical papers saying this could happen. Fortunately, reassurance could be offered. Indeed, I was one of those who wrote papers pointing out that cosmic ray particles in the galaxy had crashed together with far greater energies than could be produced in accelerators, with no disastrous effect. But physicists should surely be circumspect and precautionary about carrying out any experiments that generate conditions with no precedent even in nature. Just as I think we all agree more strongly that biologists should avoid the release of potentially devastating genetically modified pathogens. That's, I think, a real danger. So how risk-averse should we be? Some would argue that odds of 10 million to 1 against a global disaster would be good enough. Others would say that we would want even greater odds against some catastrophic disaster. And I think there is a genuine problem here, because we can bet 1 billion to 1 that the sun will rise tomorrow, etc. But if I was in front of a congressional committee trying to reassure them about an accelerator and saying the chance was less than 1 in a billion, and someone asked me, are you really claiming there's less than a 1 chance in a billion that you're wrong? I'd be uncomfortable saying yes. And I think this is a genuine issue. In fact, I think what I would say is that there may be a 1 in a billion chance of some disaster, but there's another chance of something wonderfully good coming out, say a new source of energy for the world or something. And so you're then comparing two very small numbers. And if it was 1 in a billion for destroying the world, but only 1 in a million for a new source of energy, you might think it was worth the gamble. So that's the sort of argument one would have to use. But I think we've got to be cautious, but not be paralyzed by the precautionary principle, because it has a manifest downside. And Freeman Dyson wrote another very good essay called The Hidden Cost of Saying No. And by the way, our special aversion to the risk of truly existential disasters depends on a philosophical and ethical question, which is this. Consider 2 scenarios. Scenario A wipes out 90% of human beings. Scenario B wipes out 100%. How much worse is B than A? Well, you could say 10%. The body count is 10% higher. But others would say that B is incomparably worse, because it would destroy future potentialities. As an astronomer, I can't believe humans are the end of the story. There's 5 billion years before the sun flares up, and the universe may go on forever. So post-human evolution, here on Earth and far beyond, could be as prolonged as the evolution has led to us. And therefore, B is much, much, much worse than A. And we surely shouldn't accept even a 1 in a billion chance that human extinction could foreclose that immense potential. And that's why, incidentally, we in Cambridge are setting up a centre to study these highly improbable existential risks. And that's why I'm delighted that Charlie is going to be a regular visitor to help us with this and help to save the world. Well, some of these scenarios may indeed be science fiction, but others may be disquietingly real. There's an important maxim, I think, that the unfamiliar is not the same as the improbable. And I think we therefore need to take these into account. And I'd like to finish with a nice quote from the great biologist Peter Medawar, who said, "The bells that toll for mankind are like the bells of alpine cattle. They're attached to our own necks. And it must be our fault if they do not make a tuneful and melodious sound." Thank you very much.
Okay, thanks a lot. When I first heard about this incredible group of speakers, I said, I feel like I'm going back to my high school reunion. So what I did in my youth was when these things were being discovered, because of technology advances, we could begin to see things in the sky we had no idea were there. And as we looked at active galaxies, we found these thin jets coming out from the center of galaxies and these big radio lobes. Well, Martin Rees and Roger Blandford, Mitch Begelman, quickly developed this notion of a big black hole up to 1 billion solar masses at the center of the galaxies that actually were the central engine. And therefore, we had a model that we could then begin to think about simulating. And so John Hawley, who later became head of physics at University of Virginia, and I developed these rotating magnetohydrodynamic models onto black holes. We worked with Mike Norman and Hans Winkler to show that just simple gas propagation gave most of the properties you were seeing in the lobes and so forth. But then, you know, one of the most important things was time series measurements. And here you're seeing actually going vertically from the top to the bottom over a period of time, the knots moving out along the inner jet, which enabled us for the first time to really understand these sort of nearly relativistic movements. All the last 2 days you've heard about time series, right? You measure things in time to figure out how nonlinear dynamic systems work. Well, let me take you to the next challenge. I know this seems like a non sequitur, but it turns out you're looking at the largest immune organ in the human body. This is one of 80 autoimmune diseases, inflammatory bowel disease, which, like the early days in the 70s of the radio galaxies, are described by, well, I looked at this patient and it looked like this. I did the colonoscopy, and by the way, I've got the 45-minute video I will not share with you of my last colonoscopy. And so I got into this in a very strange way, and in 10 minutes I can't tell you all that, but I was trained. I didn't know anything else. I didn't have, you know, any biomedical background, so I said, well, let's do time series. So I started taking blood and stool measurements every quarter to month for the last now 6 years or so of 150 different variables. I had no idea, of course. I was too dumb to know what I was going to find. Well, here's one, which is a very important protein that white blood cells shed as an antimicrobial as they're attacking you in an autoimmune disease. And look at these incredible oscillations about every 6 months. And at the top, that's 125 times higher than what is healthy. Now, I had no idea there was anything going on inside of my body like this, right? And I looked at a number of others, but this is the point. There is no published scientific paper in the medical research literature with a graph showing this oscillatory behavior. If we figured this out back in the early 70s, we saw something like that come out of the sky, we would have had, you know, the paper into the Astrophysical Journal on why it was happening the next day. When you look at the why could you have something like this? Well, you don't have to read too far in PubMed on the research articles to find out that you've got IBD. Now, I told my doctor, who just gave me a colonoscopy, he said, no, I've done this 30 years. I've just been inside you. You don't have it. And I said, well, you do so many of these. Oh, yeah, I do a lot of them a day. You do so many of them, you don't have time to read the scientific literature? Here's 6 peer-reviewed papers that say with a value that high, I got to have IBD. Well, fired him. Anyway, got another doctor who's one of the top, probably the best clinical researcher in the country in this, and he suggested we do an MRI. Well, this is what an MRI looks like. Slices, there's your liver, your small intestine, and you can see there in 6 inches is what turns out to be the disease part of my sigmoid large intestine. So the first thing I said is, give me the data, because these people, are just doing 2D. So I took it back home to my wizards at Cal IT2. They put it into 3D and made a sort of video game where I fly through my body, and I've given all these tours to the inside of my body. And in particular, I can just isolate the particular diseased part. I can cross-section it and see the inflammation that is taking the wall from, say, 3 millimeters to 15 millimeters. But given this technology we have today, I can then make a 3D printout of the diseased part. And Charlie, I just saw it. So, of course, you might wonder what is going on. What people like Martin and Roger Blandford taught me is when you see these patterns in nature, you have to go for the root cause. You can't just keep piling up symptoms, which is what medicine does. You've got to be a scientist or an engineer and actually understand why there is a problem. This is the technology that's made this possible. This is an incredible, once-in-a-human history change. We have had, for the entire last several billion years on Earth, DNA inside of living things. In this decade, for the first time, we can read that information out. That's beyond historic. Because what that lets us do as humans, you may not appreciate this, but for instance, if you have an autoimmune disease, there's somewhere along your 6 billion DNA, there are point defects where you've got an A or a T as a C or G. These are called single nucleotide polymorphisms. I was an early adopter of 23andMe, and here are the various ones that have been shown to be more prevalent in people with IBD than not. And there it is. I've got this thing. It's called interleukin-23 receptor. It's one of a set of cytokine messenger molecules that are involved in the center of your immune system. In fact, here's an example why if you've got that, you might think you end up with Crohn's disease. So think about this. You've got this, there's 163 of these positions along your DNA just in IBD. Okay, it's the most genetically complex disease known. So what if we could get enough people that have IBD, give them this little saliva test, we could map for the first time the difference between what was the disease phenomenology that they end up with versus what went wrong with their DNA. What is the, so guess what we're going to do? I've been working the last 2 years, and just last week, 23andMe announced we're going to get 10,000 volunteers. Pfizer is funding this so that they'll get for free. They put in their, do a survey on their how the disease is developed, and we're going to map this for the first time. Now, we're going to do this. Once this is done, just think in 5 years, every disease will be done this way that has a genetic predisposition. Now, I used to think, I did X-ray, radio, and optical astronomy observations on Andromeda, our nearest galaxy, looking for missing globular clusters in the bulge. And I thought this was pretty complicated. After all, there's 100 billion stars, right, in that thing. Well, it turns out that's 1/1000th of the number of microbes in each of you. So let's say what's complicated. I mean, I really respect astrophysics. I really love it, but it's kind of simple. And the thing is, in a human body, there are 10 times as many of these cells as there are human cells. Your human cells are 10% of the cells in your body, but it's even worse. The DNA proteins that make genes, the genes that make proteins, 1% of the DNA genes in your body are human. The rest are these microbes. So this is like the dark matter. When I got my first course in cosmology in 1969, we just assumed everything that was bright, we heard this yesterday, was the universe. Now we know it's like 3 or 4%. All of medicine ignores this at this moment. So if you think of what the medicine of 10 years from now is going to be, it's totally different. Here's an example of a person who sequenced their stool every day for a year, Eric Alm at MIT. And what you can see is these are the so-called phyla, the large groups of life for instance, all of you and say giraffes and goldfish and blue whales and so forth are vertebrates. That's a subphyla. Okay, so each of these is much more than that in its diversity. And it goes along, and it's pretty stable over here, except he flew to Thailand and started eating Thai food and having Thai germs, and all of a sudden there was an explosion of proteobacteria, namely E. coli, and as soon as he came back to the US, it went away. So this is the kind of abrupt changes that can happen. You never want to go backward, right? So, you know, I founded and ran a supercomputer center, NCSA. I used all the supercomputer. So you don't want to give that up, right? I mean, that's like one of your tools. And so it turns out that to find out who was in me and to compare my disease state against, say 250 healthy people plus, say, a couple of dozen people with IBD required 25 CPUs of supercomputer time. Taking 3 trillion DNA bases that were read using Illumina next generation sequencers by people both at the NIH and then at the Vinner Institute. Now the answer this comes up with is you take all known genetically sequenced bacteria, archaea, viruses, about 11,000 of those, times 300 people, and that's about 3 million filled spreadsheet cells. So I have these Excel spreadsheets, about 3 million filled cells each, and I just spend hours looking for patterns. And this is just to give an example of the kind of software. We're not solving the laws of physics. This is all big data analysis. We just have data, but there's this explosion in capability of being able to figure this out. So what did we find? These are, again, the phyla, and you see in healthy people, most of you are 2 phyla, basically the blue and the red, let's say it for now. But notice in Crohn's disease, that blue that's like almost all of it is this teeny little wedge. So there's been a catastrophic collapse of the ecology. And it's filled up with these other things that wouldn't be there otherwise, like actinobacteria. Over here, you have an explosion of proteobacteria. And notice I'm somewhere in between. Well, it turns out that not only did I have the SNP for Crohn's, I have the SNP for ulcerative colitis. I'm a hybrid. And there's 163 others, 161 others that I don't know yet, but we'll figure out because of 23andMe. And here's an example of what comes out of the computer. Each of these is a person. And this is a log scale from 100% to 1 part in 100,000. Look at the difference. There's no small molecule, there's no test a doctor can give you to find out if you have Crohn's or ulcerative colitis. But on the one hand, if you look at the microbial ecology, in the case of the green, which is ulcerative colitis, it's 100 times. E. coli, one species, is 100 times what healthy are. On the other hand, in Crohn's, Bifidobacterium longum, which is actually a known probiotic, is 100 times higher. So, I mean, you have to be blind to miss this. But there are, of course, no such tests yet. This is still research. So where we go next, and I'm almost done, is I've been working with UCSD, the head of GI at UCSD, Bill Sanborn, and we're building a 100-person, 150 people test to turn them all into me. So basically, we're going to do, we're going to take their blood, saliva, stool, and so forth, put it in 80 below zero chills index. We're going to sequence. Illumina just gave us a big grant to sequence all of it for both the human and the microbial DNA. But you may think I'm crazy because, but I'm actually a piker. This is the head of genetics at Stanford, Michael Snyder. And I won't go to the details, but he's doing 100 times as many biomarkers per time step, and he's done it for 40 months. Each month doing this. And this is just technology. This is what's now possible. So if you're not doing this, you're not even serious, right? So where are we going? And this is Lee Hood, who invented the gene sequencer when he was at Caltech and is now the president of the Institute for Systems Biology. He's created a project because Lee and I have worked together for 30 years. He kept watching me and he says, okay, look, let's get this, thank you, Larry. Let's do some science. And so he's got 100 people who are doing what I've been doing, and I just gave 13 vials of blood for my second quarterly bloodletting. There's our 100 pioneers is what we call, but that's going to go to 1,000, 10,000, and then 100,000. And so we'll have a population-wide view of these things and be able to tell a lot of things we don't know now. And this is really the new basis of medicine. Just to say, because we talked about having to have collaborative teams, this is the kind of team it takes to do this sort of thing. So you have medical people, computer scientists, supercomputers, genome sequencers, people that do the visualization, everything else. But it's completely doable, and every one of these things that I'm talking about is on an exponential decreasing cost curve. So while I'm doing it just to show it can be done, after all, that's what scientists do, you know, this is going to be routine in the next 10 to 20 years. Thanks.
Thanks, Larry. I didn't know that we were so much chimeras already. You know, we're not really human, are we? Into our last speaker. Heinz Stoewer is going to talk and kind of integrate everything together into systems integration.
Well, thank you, Susan. With an introduction like this, it's going to be impossible to give a talk. Nonetheless, as soon as we made this conversion from Mac into something different, I'll be getting to the subject. And the subject is really, as it comes up there, what do we do technology for, and what is the frontier of the various different fields where we advance technology in many ways. And I phrased it in a way, it's the engine for science and human progress. That's the perspective that I would like to use in this talk. So, being a good German, I follow the instructions to introduce myself. Here you see a number of former positions and current positions, etc., etc. That's part of what I do. I am a member of several industrial and space agency boards, and I'm a little bit sad at this moment because one of the companies I'm on the board launched 2 satellites last week, the Galileo satellites, the first ones of our GPS equivalent European satellites, and they went just not quite in the right orbit. So big issue, but we're going to solve that one too. If you want to know who I'm really it's up here on this one. I'm still excited about space. That's why I continue to work in space in many, many different functions. I was one of the young Germans that started space in Germany. I was 22, believe it or not, just from high school. My boss was 24, but we were all enthusiastic. We made failures. Dan, thank you for excusing me afterwards. We made failures, but we went ahead. We were fully committed, and we built a space program from zero at that time. I've been manager in most of positions that I was at, but I never wanted to become one of those managers, and we have them in this country, I suppose. We have them in Europe a lot, which is blah, 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 blah. I wanted to maintain my engineering specialty, and this is systems engineering. I'm notoriously curious about anything that develops new. That's, amongst others, why I'm so excited about this symposium, because there's so many things coming together. I'm also, to give you a little bit away where I feel as a European, I'm anxious of Europe going together faster. We have so many complexities in Europe that are all historic, that are all behavioral, and that are not oriented towards where we should be as a continent. And I truly believe in international cooperation. I've been involved most of my life in working with the US, working with Russia, working with China, working with Japan, and most all of these are very gratifying to all of the people who are involved. And looking at some of the political crises, I'm very happy to see that space is left out of the political crises in most instances, not all, unfortunately. All right. I met Charlie much too late in my life. That's one of my points. It was in the early 1990s. Charlie was running the Earth observation, the Mission to Planet Earth program in NASA. I was running the user programs in Germany, and we did some fascinating missions together and hit it off immediately on the same wavelength. Super cooperation. Ever since that, we have exciting dialogues, and we've grown very intense friendships. Charlie, thank you for that. So, 10 minutes on future technology. That's Wahnsinn. If you don't know what that word is, you'll get it as I race through my next charts. It's an impossible job. So, I have to focus essentially on context and a few examples. Now, the context to me is relatively simple. If you look at it from a broader point of view, technology has to serve. Technology has to serve ultimately the needs of population, the needs of our societies. That's why we need to understand where do we want to go, where we want to drive technology towards, namely to help solve some of the needs of our human mankind. From there, you derive what are really the things that make a difference, like health care, like mobility improvements, etc. And there, as a system engineer, we derive the system solutions to solve these needs. And if you look at this in a broader perspective, you can state that if you go down to the basics, human needs have not really changed over centuries. They're all the same, and the societal needs are also very similar around the world, except, of course, that we have a great level of differentiation, of accomplishment of what our civilization does in various different countries. So, let me give an example. Dan, I'm sorry, I have a positive attitude towards the National Academy of Engineering, but maybe that's why, because I'm not a member of it. But they've done a wonderful study, I find, namely as identifying the grand challenges, the grand engineering challenges. And if you go through those, there is quite a number of very exciting and very correct and very good things in there. Whether that's engineering better medicines, we've just heard from Larry some of the examples, or whether that's reverse engineering of the brain, there's a number of very, very good examples in there. What I particularly like is they've grouped it afterwards into 4 particular categories. Starting with the last one, joy of living. I would have never expected the National Academy of Engineering come up with joy of living as one of the key issues for the future of technology in engineering, but they did. I think it's wonderful. From a European point of view, we love it. We love our joys of living and our social comfort, in many ways different from America in quite some ways. Reducing vulnerability. That was a subject that several of you have already talked about in the last couple of days. Health, we just heard an impressive talk about some of the issues in the healthcare situation, and sustainability, a subject which has run through these days from A to Z. So that's some of the focus, the engineering challenges from which you then can also derive technology. Let me just take a few examples. Automation and autonomy, which is incidentally not the same thing, is one of the drivers of our society today. And where I come a lot from industrial point of view, because I work with various different companies in aerospace, in automobile, in other groups. And there it is very clear the automation issue is a very strong one. You've all been getting used to these kind of pictures. You have started to get some of these. What you've sensed at Google and not Volkswagen, but doesn't matter. And you've probably all witnessed this fantastic event of Curiosity landing on Mars. Other example, global logistic networks. That's where we come from somewhere. That's if you go into Bremerhaven, one of our German harbors, and look into what is being shipped in, what's being shipped out. And this is a little bit the future. It's not quite that futuristic anymore. Now, I want to introduce you to one of our German thinkings, and that's, I admit freely, a little bit a counter strategy against Google and others who are trying to migrate into the manufacturing business, trying to control and drive it. Our strategy is do it the other way around. We're strong in Germany in machine building, automobile, and many other disciplines. We say we can do that ourselves. So the logic behind this, we are moving into the fourth industrial revolution, which is obviously driven by big data, by Internet of Things, and all these kind of things. The idea behind that is, if you go back to the logistics chain or the automation and autonomy debate, you have a machine running in China, a part is getting to the end of its life. That part communicates to the factory in Germany. That factory in Germany produces the replacement part without anybody being involved. That replacement part gets shipped automatically to China, and somebody's going to build it in a week or 3 weeks later, whatever it is. So it is an efficiency improvement which we think we can make with using, or better, merging the advanced IT technologies with the machine building technologies, which we're very strong in Germany because we've never really fully believed in changing our economy from machine building into purely service. We have a marriage of the two, and it seems to work fairly well. So that's our Industry 4.0, and you'll hear much more about it in the coming years. A few other examples. If you look into the agricultural production, there's a lot of things that are happening, be that, for example, new rice species, which have much more food value in them, are much more resistant to whatever diseases can affect them, are more stable against weather implications, etc., etc. And, of course, productivity advancements, in part supported through space observations, because we can direct the farmers. This one needs a little bit more of dung, whatever dung the English word for dung is, and this one you don't have to water as strongly, economizing the agriculture production and feeding more people. And it's not a 2%, this is a 30 to 40 to 50% improvement in the productivity, therefore being able to feed something like 30 to 40% more people on this planet. Another one, healthcare. We just had a wonderful discussion on this one. If you look at it with a little bit of distance, the non-invasive diagnostics have made an enormous jump in the last 20 years, and it's going to go on. And every one of us appreciate being diagnosed without being put something into our body, etc. Or the new chips which are getting into your body, and the left example you see here is a little chip that can regulate for 16 years the pregnancy situation of a woman. A fantastic improvement, not yet on the market, but it will take another 3, 4, 5 years, something like that. And the last example back there is brain-directed robotics. This is an example of a DLR robotic instrument where a lady has been wired in her head. She was totally paralyzed, but with her thoughts, she is moving this robot to give her Coca-Cola, purely through thought power. These are wonderful examples of where the technology is going and what is hopefully going to happen in the few things. Global technology enablers, telecommunication, Internet of Things. I don't think here I have to say a lot about it. You're all totally aware of it. And smaller, lighter, faster, or then faster, better, cheaper is everywhere. You are totally right, even though I know you were criticized quite a bit for that statement for lots of reasons, but you are totally right. It's not just in space, it's happening everywhere. If I work with BMW, for example, or other companies, their credo is faster, better, cheaper. And that's the difference in being competitive or not. It is everywhere in industry, whether you look at software industry, whether you look at machine building industry, that's driving industry everywhere, whether that's in South Korea, in China, in US, or wherever. Another example, integration of what I call hard and soft science disciplines. Charlie's made several allusions to this one, and I'm quoting here Charles West. He made a wonderful lecture when he was at our university in Delft a little while ago, in making exactly the point. We have what I call the hard sciences, which is micro, bio, info, et cetera, and we have the soft ones, which are healthcare, communications in part, energy in part, et cetera. The fundamental point is we need for the systems of the future, and these systems of the future will be more system of systems than we've ever had before. We need to bring all of the fractions together. The social fraction, the environmental fractions, the natural sciences fractions to solve the issues which are before us. And one of my last examples is the history of understanding where we're going, where we come from. And I'll show you just a couple of charts of something you may not have seen yet. This is a comet which races through the plasma. And when we saw this picture first, everybody was totally astonished. It's taken by a probe which has gone 6.5 billion kilometers through space, was on its way 10 years to arrive at a comet that's racing through space with about 16 kilometers per second. We rendezvoused with it on 6 August, and we found lots of astonishing things already. For example, how can a body which races through plasma can be so totally asymmetric? Nobody, probably not even Martin Rees, would have expected that to happen. Everybody is totally baffled. How can such a body run and race through space for hundreds, for millions of years and have that kind of a shape? And if you look a little bit closer, it has surfaces which were totally baffling. Flat surfaces, boulder surfaces, all kinds of features on it which nobody really understands yet well. And worse, not worse, we're attempting to land on this body which nobody really understands very well. Somewhere up here or there, they're just evaluating the different landing spaces.
How big is this?
This thing is about 30 kilometers or so. And landing on something which has practically no gravity is a particular nonsensical operation. Because every moment, as Newton tells us, you impart, gets a counter moment, it throws you off immediately, as no matter how softly you touch down. So what we're trying to do is send harpoons in there, anchor it before it can go back up again. But try to put an anchor in something which you don't know whether it's hard rock or soft snow. So we're in for a challenge. So 11 September, cross your fingers. And incidentally, communication is almost 30 minutes. So this thing is totally autonomous, is landing all on its own, etc. So just a few examples to specific technology drivers. Now, I've been thinking a lot about what is common of all of these examples. What can I give you for your own mental remembrance? And there's one thing, the multi or interdisciplinary approach. The future on systems, certainly, and the future in technology is getting various different disciplines together and getting this little thing here organized, man and machine, mechanical, intellectual, other powers together. What is the balance going to look like? This is an extension of the thought of Charles West in that respect. The second one that might surprise you, maybe not quite so much. This is virtual worlds, models, simulation. Now, on the science side, modeling and simulation is a basic tool since many, many years. On the engineering side, We have a lot of specialized tools, but we have, for example, none to really evaluate complex systems. And complex systems, such as environmental systems and others, are extremely hard to fathom because there's lots of soft and hard elements coming together, trying to find the right kind of balance, what we call the system optimization. But the last example is global developments. I know in the US you think sometimes differently. You're a bit focused on your country, which is wonderful. In Europe, we can't quite focus just on one country because we're much too small. The global interaction, the global interdependency, be that on research networks for technologies, with Singapore, with California, with Germany, with Russia, whatever, and the interdependent economies. They are, amongst others, also an ingredient for better understanding the world and being more compatible. So, some of the examples I've used are in a document called INCOSI Vision 2025. INCOSI is the International Council on Systems Engineering, which is the worldwide organization, Systems Engineering. There's a contribution from Charlie in there, a very important one, namely he's put his finger onto the system of system interactions with engineering and sustainability, et cetera, et cetera. So, Charlie, the first copy, I know you haven't seen it yet, is here. So the personal note is there for you. Now, firstly, Charlie, thank you. Bringing us together here is very stimulating, as you are stimulating all the time when I talk to you. I know you didn't want any presents, but you know, sometimes I'm a German with an Eigensinn. I follow instructions to the point that I think they make sense, but I dug into your past life, something of the dark side which you maybe have forgotten or you've pushed away. And it is documented by this picture. It shows Charlie crossing the Iron Curtain, but he thought he was undetected, but that wasn't quite true. And if you don't quite believe this is Charlie, I'll get you the proof. In fact, they caught him, they investigated him, and ever since, they called this one with a very particular point, namely Charlie's checkpoint. Checkpoint Charlie. And the little present that I'm handing you now is from Checkpoint Charlie. And it stands for lots of things, and you're the first one to really understand it. So we had these 2 days, Checkpoint Charlie, of an entirely different one, but this one is even more historic than you ever thought. Charlie, this is yours.
Fellows, okay, one of our senior fellows. So we represent people at the highest distinction, and we give them a focus of getting their information through to policymakers who are making decisions. So great group, and we've been talking a lot about the past, the history of Charlie's work. Well, let me tell you something that's really current. I mean, current like as of today. So yesterday, our organization released a report on hydraulic fracturing. This was a report that was commissioned by the Bureau of Land Management, and Charlie, as chair of the board, was deeply involved in making sure that we had really good science, and we had only science that was verifiable, peer-reviewed, conflict of interest removed, and all the things that we know how to do as scientists. And Charlie was really in charge of that. And as of today, Charlie, today it's in 60 media outlets. It's in the LA Times, it's in ABC News, it's NPR, it's all over the place. And as a consequence of the work that was done, And the Bureau of Land Management has announced that it's going to start relicensing for hydraulic fracturing starting in 2015. And it's based on the data that we said that we knew, but more importantly, the data that we said that we didn't know. Because this report clearly says what we don't know and what we need to measure going forward. And so it's just come out that the Bureau of Land Management is going to go forward. This work is built on a whole bunch of reports that Charlie was also involved with. We've talked a lot about greenhouse gases and about energy and about the future of climate change. So we've done a whole series of reports which translates the science into the policy and looks at it through the eyes of policymakers such as those who created AB 32, the greenhouse gas emissions legislation, and also for the executive order that we're looking at. And the most important thing here is that we do a systems engineering approach, because we look at the whole system. We don't look at anything in isolation. You can only count an electron once. So we look at the whole system going through, and this work has resulted in not only legislation, policy changes, business changes, all sorts of things. So the council is fortunate enough to do profound things. We also do things that we didn't really want to do, but we had to, like look at the efficacy of detecting cell phones in prisons, for which we went round.
This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
Hello, hello. Good afternoon. My name is Susan Hackwood, and I'll be moderating this next section. And this is the next to last one before us and cocktails. We have a spectacular group of people who will be talking. But first, before we go forward, let me tell you something about the secret life of Charlie Kennel. Okay, so you know, I was listening yesterday and today, and in my career in engineering, I've touched on some of the subjects that were being talked about, but it was absolutely wonderful to be with the people who were really there generating those new ideas. I felt like I was in an Entmoot, you know, which is in Middle Earth, where all the sage trees get together and discuss the future of the universe. So it was a wonderful experience. I've had the pleasure of working with Charlie for a decade or so now, maybe longer. And I work with Charlie in a totally different context. So can I just take 2 minutes to put that in context for you? This is part of Charlie's secret life. Charlie is the chair of the board of directors of the California Council on Science and Technology. And the council was formed in 1988, and it's modeled after the National Research Council. And the basic goal was that we have so many really good scientists and engineers and medical doctors, et cetera, in California. And there's really a vacuum in how that body of knowledge is used in policy making, particularly in the state government. We're good at sending people to NASA or sending people to Congress or sending people around, but we're not good at sending people to Sacramento. Yet there's so much in charge of our future, and particularly of our infrastructure and what goes on. So the council was created. It's an amazing organization. It represents about 250 people of the state's science and technology leadership. Julie Meyer-Wright, who's in the audience over here, is one of our council members, and I don't know where Bob Dines went, but Bob is one of our senior things that are the disruptive technologies that are truly affecting us now. This is from a McKinsey report. I won't read these things, you can see them, but you know that these are the things that are deeply affecting everything we do in society and everything that we do in our life. I'll give you just a couple of examples. This is from the MIT Sensibility Lab, and what it is showing how mobile networking is redrawing communities. So, and Larry, you know a lot about this, but the bottom one is a density map of the population in the US. The second one is the frequency of connections of cell phone and text messaging between communities. And the top one is a density map projected up onto that. And you can see that the United States is changing its boundaries. And we can confirm that Northern California does not talk to Southern California. We can also confirm that Texas talks to no one. And we can also see that the East Coast and West Coast, the coasts have got a close connection. So those are the sorts of things that are redefining our society. Everything we do, how we connect with people is changing. Our young people have got a very different way of introducing each other. And there's no such thing as a blind date anymore. We also have come to rely on machines in a different way. So do you remember Clippy? Clippy, 2003, Clippy came out. In 2010, Time magazine voted it as one of the 3 worst inventions ever. It was dreadful. Remember, as soon as you wrote dear, it would pop up and bug you. So we've gone from that to Samantha and Siri. Anyone see the movie Hair? Yes. Okay, so in Hair, the protagonist is love forlorn and falls in love with his system on his cell phone. It's basically a Siri, and they have a very strong and long relationship with each other. So it's happening, the changes that we're seeing in society. We're seeing super changes in medicine. Surgical robotics is on the scene, and it's not going to go away. Telemedicine is definitely there. And we're beginning to see the drone wars. And you know how the drones are used in the military, and this is an example. MIT has a little helicopter in the prisons in California. So we will do anything that the state is asking us for. And most important over the last few years, and this is under Charlie's leadership, we've started a program where we place 10 recent, fresh PhD graduates from science and technology into state legislative offices, where they get to learn how the sausage is really made. They become the advisory, science advisory for that committee or for that legislative office. And they come from all over the place. They come from our best schools, Berkeley, Carnegie Mellon, Cornell, Columbia, you name it. We've got students who have come through here and gone through this process. And what's interesting is that more than half of them, more like 70% of them, stay in public policy. They switch from a promising career in science or technology and stay in public policy. Why? Because they see how much they're needed. They are responsible for literally hundreds of pieces of legislation and even more hundreds that don't get passed. So along those lines, this is special because Senator Fran Pavley, for any of you who know who she is in the state, she's a very powerful senator. AB 32 came out of Fran Pavley's work, and she is the Senate Natural Resources Committee chair. It's she who has got the legislation on hydraulic fracturing for SB4. And I show this picture because these are her right-hand people. And the young lady who's standing over to her left-hand side is Tony Lee, one of our current fellows, who has her PhD in biochemistry and molecular biology from Caltech. And she's so special, she gets to walk the first dog, Sutter. So that's Sutter. So that's another aspect of Charlie's secret life where he has truly helped translate the wonderful science that he knows so well into the hands of policymakers who can actually use it and become a known and trusted entity in that. So great. We were given the task in this session to talk about the technologies and science of the future. And I use this analogy. When I was at Bell Labs, we talked about pots and pans. So pots and pans are plain old telephone service, and pans is pretty amazing new stuff. So we're going to get to talk about some pretty amazing new stuff now with our speakers, and then have a roundtable discussion afterwards. And many of you know the kinds of helicopter that you can call up on your cell phone, and it will come and you say, I want to go to lab so-and-so, and the little machine will come afloat in front of you and say, oh, you want to go to lab so-and-so, I'll take you. And you follow it, and it'll take you there. So And you know Amazon is going to use this as drops and things. Yeah, right. So, this is the kind of society we live in. And I'll finish with this, the genomics with 23andMe and all the other things. And Larry is going to talk about wiring yourself up. You can find all sorts of things out about yourself. So I've discovered that from 23andMe, I have less of a percentage of Neanderthal in my genome than other people. So Steve Jobs was a visionary, and some of you might like him, some of you might not like him, but he got it right about how inventions happen and how creative things happen. And the people that we're going to have now talking are on the forefront of these things. And so in order of where we'll go, we're going to have Louis Branscom's talk first, and on forces of science and technology. We've got Martin Rees, who's going to talk about catastrophes and risks. Larry Smarr is going to talk about digital transformation of medicine. And then Heinz is going to wind us up with technology engine for science and progress. So with that, I'll keep quiet and invite up Louis.
Thank you. Well, I came out to this wonderful La Jolla place in 2005 for very good reasons. When I came along, just to give you a word or two about my background, where I come from, as an emeritus professor in public policy and corporate management at the Kennedy School at Harvard. You may have thought I was a scientist. That doesn't sound much like a scientist, although the corporate management part of that title probably reflects the 15 years I spent as chief scientist and vice president at IBM. In any event, at the Kennedy School, I was the director of the Science and Public Policy program there, following in the footsteps of the great Harvey Brooks. In those days, whenever I was at a meeting and somebody asks, "What are you doing?" I say, "I'm the understudy of Harvey Brooks." I don't know many of you how know him. I think he's now deceased, but I think he's the best and strongest science policy person